أعتقد it's now. It's now okay. Good.
ممتاز.
Good. Okay. Go back to the lecture. So fracture toughness or the KIC or the damping property or the toughness of the material can be tested by different mechanical testing, different configuration, and based on the configuration we do have Charby test and Azor test. Also, altering load or oscillating load, subjecting the material to oscillating load can be tested to get out the fatigue property of the material or the fatigue behavior of the material by applying altering load and compression and tension and compression and tension and so on. So we do have a mean load, a mean stress, and then we do have altering the load up and down this mean load to cover compression area, tension and compression area, or tension area only. The outcomes of this test is endurance limit, which defines the number of cycles that get the material failure. And also we can construct this graph to follow the fracture during the fatigue test. Furthermore, creep can be tested, and the creep simply is the subjected the material to a particular load at elevated temperature, and then get the outcomes is getting the 3-stage of creep and define if the material is time dependent behaved or time independent behavior. Finally, of the most important micro scale testing is the hardness testing, when we force an indenter with different shape to penetrate a surface and then measure the impression diameter or surface area to get the hardness of the material. So far we are talking about macro scale mechanical testing, and that being used for testing or for characterizing the bulk material. But the question rises here: how can we test the thin film that deposited on the surface? How can we test the surface treated material, or how can we test coating? We can't do all these tests by using the already mentioned mechanical testing. And for this, or we can extend our question to ask, how can we test the material in nanoscale? Test the mechanical property of the material in nanoscale.
راح الشيرنج مالتك دكتور رغدان عيني.
والله يا دكتور ما ادري، يعني انا اركز بالهذا وما بعد ما ابغى اشير
مالتك.
يعني شنو المشكله يمي والله ما ادري.
يلا مو مشكله.
يلا ممكن.
يلا اوكي شو بس اليوم ما اعرف.
والله دكتور على مودك زيت الاشتراك مالتي.
يلا اوكي عاشي.
هذا الاشتراك مال الانترنت غيرته على مودك.
يلا اوكي خير.
هذا بال 5000 اشتراك يلا.
لا دكتور سويته بال 50 وقلت لك انا سويته بال 50.
يلا توكل.
Okay, so we've been talking about the general mechanical testing for bulk material, and we need to define a new way to test the mechanical properties for coating, for surface treated material, for even for thin films, or even for the nanoscale material, or let's say we do have a composite material that has a fiber in nanoscale, and we need to test the individual fibers in nanoscale. How can we do this? Actually, the answer of all these questions comes with what is called instrumented indentation, or the indentation that been fully instrumented, or what is known in the scientific community as nanoindentation. Nanoindentation is a compact machine, tabletop machine, small machine, that has the ability of the configuration is quite similar to hardness testing. We do force an indenter with different shape to penetrate the surface and then leaving the surface. But the difference, the significant difference between this nano indentation or this machine instrumented indentation, this technique, and the other hardness test, that the process from time zero to the final minute or final second of the test is fully controlled and recording. So the test is performed under fully control, fully computer control, from the very beginning of the test to the very end of the test, with high precision. The other advantage, high precision, in such a way that the load recorded in microscale, in micronewton scale, and the distance recording in nanometer scale, in nanoscale. So under this configuration, the tabletop or the compacted machine needs to be kept inside a box and needs to be bought on anti-vibration table. These box and the vibration table are used to eliminate all the effect of the environment, thermal effect of the environment, vibration in the building, and so on. So putting the nano indentation inside box is crucial, and you can't rely on any test without doing so. Okay. So what is the theory, the basic theory of the indentation? Actually, the indenter, which might be with different shape, is connected to an arm, and this arm is connected to actuator. Actuator basically is a part of the nano indentation, of the part of the machine that create the motion we need for the indentation. So then, based on the manufacturer, we do have piezo actuator, and in other manufacturer companies, they use coil fluctuator. The arm that hold the indenter is also connected to load cell, and as we mentioned earlier, the load recorded here is very precise. It is in microscale, and then it's connected to a capacitive sensor. And the capacitive sensor basically is two parallel metal plates that can measure the capacity of the air between them, and any changing in the position of them means changing in the capacity of the air between them, and these reading or these raw data can be converted to distance in nanoscale. And nanoscale accuracy. Okay. Now we do have many indenters, starting from Vickers, Barkovich, Knob, and so on. Ball, any one of them. But among these indenters, Barkovich and Ball indenter have got a lot of interest. And most publication of the nano indentation use these two indentation because they are very well defined in terms of area of contact, and they can perform very high precision indentation test with very high precision results. Now let's think about the results that come out from nano indentation. 1 minute. the raw data that comes out from the nanoindentation is basically the load from the load cell and the distance or the displacement from the capacitive sensor. Okay, so the load, we do have raw data comes out from the machine, which is the load and the displacement or the depth. And as long as mentioned earlier, everything is recordable, everything is done under fully computer control. So we will have, when we loading when we push the indenter to penetrate the surface, we will have increasing of the depth with load. Okay, quite understood. And then we reach the maximum load, the maximum point of the load, and then after that we start to lift the indenter from the surface. So we will get the unloading curve. Loading segment and unloading segment. You have two segments. Unloading segments when we increase, when we push the indenter to penetrate the surface, and unloading segment when we lift up the indenter from the surface. Everything is under control. Again, everything is under control. If we think about this curve, now this is the maximum penetration depth, and when we left the indenter from the surface, this distance decreases with the load until it's for every single material. As for I'm coming in the discussion, in the coming discussion.
أحباء إذا تسمحوا لي أسئلة بنهاية المحاضرة رجاء. دكتور رغدان تفضل حبيبي عيني تفضل.
Okay, sure. So the unloading segment, when we think about unloading segment, which is the most important segment of the curve, when we decrease the load, the depth, the distance. أعتقد
دكتور رغدان صوتك ماكو ما نسمعك. دكتور رغدان.
دكتور علاء بلده.
Okay. I fix it. Sorry, I fix it. دكتور بس ابقى تابعه يعني خاف الصوت ينقطع او شيء. تمام. So they وين توقفنا عفوا دكتور؟ وين توقفنا؟
هنا بنفس المكان ما صار القطع زايد يعني دقيقة واحدة بس يعني مو أكثر.
Okay. So the most important segment of this simple curve is the unloading and the unloading segment. And if you think about it, when we decrease the load, the depth of the penetration decreases. And as everyone knows that when we are even inside the plastic deformation, even inside the plasticity region of the material, we do have elastic deformation. And by doing nanoindentation, we can separate the elasticity property or the elastic deformation from plastic deformation. And this is one of the most advantage or most powerful advantage of the nanoindentation. Okay, so the distance, the recovered distance from the maximum load, the depth from the maximum load until the depth at the final point is ascribed to elastic recovery of the material, right? It's elastic recovery. There is an elastic recovery of the material when we left the indenter from the surface. The distance from this point to this point, the point when the curve intersects the unloading curve intersect the x-axis and the original point represents the plastic deformation. So we do have two areas or two lines here. One represents the plastic deformation and one represents the elastic deformation. Based on this theory or this results, we can roughly estimate how much we do have deformation as a plastic deformation and as a elastic deformation. This couldn't be found by using any other technique. So we can't by using any other technique, we can't separate the elastic deformation and the plastic deformation with high accuracy like what we are doing here in nanoindentation. Now let's go through some calculations, some small calculations. This is the P distance, the load displacement curve, and loading segment, unloading segment. The hardness is defined as P over A, right? Hardness is defined as P over A. P here is the maximum load that we performed during the test. AC is the projected area or the contact area, the projected area of the contact area. And this area, as long as we are using very well-defined indenter like Barkovich or Ball or Vickers, we can take the AC as function of the depth, as function of the penetration depth of the indenter. And it is after doing some math, we can get 24.5 times HC square for Barkovich indenter. So AC is defined by this equation for Barkovich. We do have another equations already derived for Ball indenter, for Vickers indenter, for Knob indenter, and so on. Now, the important thing is that HC is not the depth. The depth of the indenter is not defined as the depth of the indenter. HC is a function of the H max and P over S. And we adding epsilon here, which is the factor that depends on the shape of the indenter. For each indenter, there is an epsilon. There is an epsilon, a particular epsilon for each shape of the each indenter, Ball, Vickers, Ball, Vickers, Barkovich, and so on. The key point of this equation is S, which is the contact stiffness. Contact stiffness is the first thing that we need to get before starting our analysis. The contact stiffness, S, can be determined by getting the slope of the initial portion, of the unloading segment. This is the unloading segment, and this is the initial portion of the unloading segment. All we need to do is getting the slope of it, and the slope represents S, the contact stiffness. And by getting the contact stiffness, put it in this mathematical equation, we can get HC. I'm talking about the procedure of the getting the mechanical property from the nanoindentation curves, or from the results of nanoindentation. So S is the first to be found from the curve, from the load displacement curve. S again is the slope of the initial portion of unloading segment. By getting S, we can get HC, and by getting HC, we can get AC, and by getting AC, we can get hardness. Okay, so the first step is getting S, then HC, then AC, then H. But remember, H calculated here represents the real H of the material, the real hardness of the material, because we eliminate the elastic recovery of the material that we can't do in hardness and traditional hardness test, because in traditional hardness test we take an image for the impression, and based on the diameter or the two diameter, we can calculate the hardness, totally ignoring the elastic behavior within the material. And as long as we can separate the elasticity from the plasticity, we can get some information about the plasticity by using this equation. S equals to beta times T times 2 divided by the square root of pi times reduced modulus. I will go back to the reduced modulus times the square root of AC. AC already gotten from here. Beta is another factor, is another constant that depends on the shape of the indenter. And reduced modulus. If the audience have an idea about what's called contact theory, Hertzian contact theory. So when we contact when two material come into contact with different material, for example, in our example, we do have diamond contacting metal, for example. So the different modulus for the two material, we do have different material for the two material, and when we push them together, close together, we have what is called the reduced modulus, which comes from the modulus of the two material, which might be very hugely different from the two material. For example, we are using diamond with very high elastic modulus with metal with ordinary elastic modulus, and by this equation we can get reduced modulus, and putting the reduced modulus in this equation, which is Hertzian contact theory, we can find the modulus of the elasticity for the surface. Don't worry about all these calculations. The software that provided with the nanoindentation does all this stuff for you. So the result, the raw data comes from the machine as P and the distance, the load and the distance, and then the software analyzes this data and gives you the hardness of the material as mechanical property representative for the plastic deformation of the material, and the elastic modulus as a representative for the elasticity of the material. So don't worry about all these stuff. It's just going through the theory of the machine very, very quickly without derivatives or without all these mathematical stuff. So what I want to say here, that by doing a standard test, very simple test, very simple nanoindentation test, you can get out the hardness of the material and the modulus of elasticity for the material with high precision. Again, there's a highlight for high precision. High precision. There is no way to compare the results from this machine with others. No way. no effect. If you do the test correctly, there is almost zero error in the results of this machine of this results. Okay, this is the traditional test of the nanoindentation. Is it the end of the story of the nanoindentation? Of course not. It is only the beginning. Only the beginning. And we do have many other modes that we can, by using them, we can extract different mechanical properties. The idea here, nanoindentation, is everything is controllable. Everything is controllable. And we can apply different load function for the indenter, different load function on the indenter to extract different mechanical properties. And we will go through the important load function that we are using in nanoindentation and what are the mechanical properties that we can extract from them. Okay, now there's a mode in nanoindentation called constant stiffness measurement. And for this load, mode, sorry, instead of applying constant and incremental load in loading segment as we are doing here, we are applying a constant and incremental load for the loading segment. Instead of doing this, we can do it with applying sinusoidal load. So the load is not continuously increased, but it increased with applying sinusoidal function, load function. And the purpose of this is that in every single sinusoidal segment or every single sinusoidal cycle, we do have unloading segment, and from unloading segment, we can determine S, and from S we can go through all the calculations that already mentioned in the last slide. So the idea is applying a sinusoidal incrementally increased load for the loading segment and get the mechanical properties for every single point of the load. Every single point of the load can be defined in terms of hardness, contact stiffness, and reduced modulus. We can use the results of this sophisticated technique to build up stress strain curve and define elastic region and the plastic region by following this procedure. So the outcome of the machine is P and H, the load and the penetration depth, and we can get HC from them, and then we can get AC from them using the same procedure that already mentioned, that already described in the last slide. And then I forgot to mention that this test is performed with using ball indenter. Ball indenter. It has to be done by using ball indenter. So until here, we are following the same procedure of the traditional testing, but here there's an adding steps to calculate the A, which is the radius of the contact. The radius of the contact, and from the radius of the contact, we can follow these mathematical equations to define stress and strain. So we do have, by following this procedure, we do have the stress and the strain at every single point of the loading curve. And by putting them in this curve, we can define stress, or we can build up stress-strain curve for the material. But remember, this is called the indentation stress-strain curve. Indentation stress-strain curve. It can be used to define the modulus of elasticity with high accuracy. It can be used to define the yielding point, but there is a debate about the plastic behavior of the material. For example, N, what's called N. I forgot the name of N. Forget it. The power of the plasticity. When we define the plasticity, we do have N as a constant, which is I forgot it. So we can't use this curve to define N because it is under debate, and there are some researchers use finite element to find N by using this curve, but it's still under research. So don't do it. It's still under research, and the validity of the test is not that high at the moment. But at least you can define the yielding point with high accuracy. Yielding point. So we got you got the modulus of elasticity and yielding point with high accuracy. Constant stiffness measurement is also used to measure other mechanical properties. For example, creep behavior. How can we do that? By applying a load, or raising the load at a particular point, and then hold the load at that time. But during the holding, we can apply constant stiffness measurement, or we can apply an oscillating load at this holding segment. And by doing so, we can measure S and hardness and modulus of elasticity at every single point of time. And getting the results as here. Here the mean stress is the same as hardness. So what we are doing here is measuring the hardness at every single point of holding segment, and measuring the hardness of this and monitor it. If there is decrease in the hardness during the time of holding, this means that the material time-dependent mechanically deformed material, or the creep behavior of the material is defined well for this material. This mathematical equation, sorry?
عندك 12 دقيقة بعد بس.
الله كريم.
Okay.
الله كريم. So the mathematical equation that used to do so is here for your information. So we are using this mathematical equation to define the hardness. The contact stiffness already defined from the constant stiffness, from the outcomes of the constant stiffness measurement. Okay. And as long as we fully control the indentation movement, and as long as we can do an oscillation load, altering the load, of course we can do fatigue testing, nano fatigue testing. And this technique is crucially important to characterize the treated surfaces, the mechanical property of treated surfaces, the coating, the thin films, and so on. So what we are doing here, we raising the load at a particular mean load, and starting to oscillate the indenter with different frequencies. Depends on our application. So, for example, here we are testing a material. We are testing a material at a load amplitude here, 4 micronewton load amplitude, and we found that after infinite time there is no failure for the material. With increasing the load amplitude, there is a failure point which can be detected from the reduction in the contact stiffness measurement. With increasing the load further, the point moving to the left point until it gets here. What is occurring, or what is the mechanism of the failure for coating under fatigue test is either get fracture of the surface, or get the coating de-eliminated or delaminate from the surface. So the fatigue test, nano fatigue test, is crucially useful to test the adhesion of the coating with the substrate as well. So it is used to measure the fatigue property, or to determine the fatigue property of the surface, but also used to measure the adhesion between the coating material and the substrate material. Another important mode for the nano indentation. I'm going very quickly through the application of the nano indentation because the limitation of time. It's only 1 hour. So I'm going very quickly. For further information, you can contact me, or I can send you some extra literature to define it, to get more information. So DMA. I guess everyone knows DMA. What is DMA? Dynamic mechanical analysis. And when we talk about DMA in nano indentation, it's called nano DMA. Nano DMA, or DMA testing, is used to recognize the storage modulus from the loose modulus. And this is very important and has a significant importance in polymeric material. So we can apply load and then oscillate the indenter with different frequencies and get the effect of each frequency on the material. Complex modulus, which is a combination of storage modulus and the loose modulus, or for the material, for the people who haven't heard about it, it's for the material that has elasticity and viscosity, viscoelastic behavior. So the increasing in the storage modulus means increasing in elasticity property of the material. Increasing of losing modulus means increasing in viscosity behavior. The data get out from the machine is the recording the load and the load and the displacement. And from recognize the in phase out of phase, we can determine the storage modulus and the loose modulus by using this formula, which is simply, we can get it simple. It's complex modulus cosine delta and sine modulus times complex modulus. Okay, so delta, the delta. The phase angle, the angle delta is the phase angle between the complex and the storage modulus. For tire industry, this is very important because when the vehicle move on a tire, the frequency of the load, the frequency of the cyclic loading depends on the how fast the vehicle. With increasing the speed, the frequency increases. With decreases, the frequency decreases. So the manufacturer needs to know what the effect of this on the mechanical storage modulus and loose modulus. Okay, so they bring this case to nano indentation, simulate it or mimic it inside the nano indentation, apply DMA test, and they found that with increasing the the applying load or the speed of the vehicle, both loose modulus and storage modulus increases. It is also important in the same industry, tire industry, because tire industry, most of the successful manufacture of tire industry are the fibers, microfibers or even nanofibers, to enhance the behavior, the performance of the tires. And as everyone knows, this fibers do not distribute homogeneously in the tire. They deliberately add them to a particular point of the tire to increase the storage modulus, and left out the other parts to increase the loose modulus or the damping property of these parts of the tire. So we can again bring these cases in our these industrial cases in our nano indentation and test them out to check out if the distribution of the fibers are correct or there is a failure in it. Also, DMA is used to find out a glass transition temperature, or TG, glass transition TG, or even gamma transition or beta transition, which all related to polymeric material, when the behavior of the material of the polymeric material change with the temperature. So all we do here is adding a chamber, heating chamber to the nano indentation and applying the DMA function and increasing the temperature until we detect one of these three events. So the TG can be the TG beta transition or gamma transition can be detected by sudden degradation in storage modulus, or by having a peak in loose modulus, or by having a peak in tan delta. So having one of these events means that we do have either beta transition, delta transition, or TG. And this after comparison with other thermal testing has found very accurate, because under nano indentation we are testing the mechanical property with, as we mentioned earlier, with very high accuracy, and all these transitions, all these delta, TG, beta, gamma transition, all these related to degradation in the mechanical properties. So we can also detect this degradation in the mechanical properties by using nano indentation. Fracture is another story, successful story that we can test in nano indentation, and all we can do here, it is limited to brittle material. We can do fracture test for the ductile material by using nano indentation. So far, I don't know what's going to happen in the future, but so far we can test the fracture toughness for the material. For every single material, only for brittle material. It's quite simple. All we do, we perform a standard test, loading segment, unloading segment, and if there is a fracture, there is a sudden change in the loading segment, and these events are called pop-in events, and they always refer to fracture occurring in brittle material. For ductile material, these pop-in events always refer to activation of dislocation system. So under a certain load, there is an activation of a certain dislocation system, sudden movement of dislocation system. But now we are talking about a brittle material, so the pop-in refers to the fracture occurrence. Some nano indentation instruments are equipped with the acoustic emission sensor. So the acoustic, what the acoustic emission sensor does is listening to the material, and when there is a sudden acoustic emission, it records. And here, the sudden acoustic emission is fracture occurrence. So we can define the load that that causes the fracture of the material. Also, there are many mathematical equations uses this information to determine KIC for these material. More advanced, some nanoindentation instrument is designed to be very compacted in such a way that we can insert them inside scanning electron microscopy. And when we insert it inside an electron microscopy, we can do the whole test inside the electron microscopy. For example, sorry. Okay, good. I thought I lose the connection. Okay, so inside the SEM. Inside the SEM, we can use a mode in SEM called focus ion beam, when we can make different shapes inside the SEM, like this shape, which is called micropeller. And then, by using the nanoindentation, we can push this micropeller under control by using a flat punch. So we do have flat punch for the nanoindentation, and push this down, this micropeller down, and monitor it, as we can see here, monitor it until get some fracture. This also synchronized with recording data from the nanoindentation, so the outcome of the machine is high precision stress strain curve, and whole recording of the test, imaging recording or video recording of the test from 0 time to the end of to the fracture occurrence. Even more advanced, the nanoindentation is compacted to be inside TEM, transition electron microscopy. And as you can see here, this is the indenter, this is the material, and when push the indenter toward the material, we can monitor all the mechanical, all the events of dislocations, of changing in the grains, and so on, by using this technique. Actually, I've been in a conference in 2018 about using nanoindentation inside TM, and I met some PhD students worked for 3 years only to get a good video about nanoindentation. So all their work is applying like this test and finding out what is the behavior of the material under compression. So in the end of their PhD, they produce only a video, and discuss the results of this video. So far, we are using one-dimension load cell. We can exchange this one-dimension load cell by two-dimension load cell, and perform a scratching test. And scratching test is moving the indenter on the surface, on the coated surface, or on the surface from 0 load to the maximum load. And monitoring the events like coefficient of friction, the depth, and here acoustic emission. So when there is a sudden increase in the coefficient of friction, or a sudden decrease in the depth, or an increase in the depth, and a sudden acoustic emission, this means that there is a fracture, or there is a delamination of the coating. For example, if we are testing coating, so very accurate test for scratching and even for wear. Because wear, as you know, wear is a multiple pass, multiple pass scratching test. So we instead of doing one pass scratcher, we can do 10 passes, and we can define the wear property of the material. Imaging can also be performed by nanoindentation. We do have two kinds of imaging for nanoindentation. One is getting the topography of the surface by tapping the indenter on the surface, scanning the surface, and finding out the topography of the surface. This is not important because the accuracy of it is not that much in compared with AFM. So as long as we do have AFM, so this way is not important. We can pass it, but the importance of imaging in nanoindentation is what's called modulus mapping. And during modulus mapping, we again tap the surface by the indenter, and at each single tap, we measure the elastic property. The load of the tapping has to be very small, yet it has to be enough to get the response from the material, get the elastic response from the material. Here's an example from my own work. So the material is dual phase material. Dual phase. This is a phase and this is a phase. So we do a modulus mapping for this material, identify the two phases, and then we determine the effect, the strain rate effect. The strain rate effect on the two phases. So we can determine the strain rate effect on this phase and on this phase. The work is under publication, so I can't give you any results of this material. Sorry for that. I guess I reached the end of my presentation, and during the presentation, I know I was so fast, but the time limitation and the huge information that I want to present here makes me that fast in my presentation. I'm open for any questions or comments or any concerns about using nanoindentation. Thank you very much for your listening.
Okay, thank you, Dr.
شكرا دكتور.
All audience have a very clear lecture. تفضل دكتور رابط.
شكرا جزيلا دكتور رغدان. إذا أسمع it is a rich الحقيقة information و valuable information، وإحنا نشكر الدكتور رغدان على المحاضرة. So nice presentation. الحقيقة أنا عندي يعني بعض التساؤلات البسيطة وأترك المجال للأخوان. كنا نتمنى أن حضرتك حتى في المحاضرة القادمة تعرض لنا a short video about the tensile and the compression test للنانو ماتيريال. الحقيقة أنا مدى أستوعب ومدى أتخيل كيفية إنه إذا تجري عملية compression أو tension test. هاي النقطة أتمنى إنه تعرض لنا فيديو في هذا المجال. هاي النقطة.
حلو لطيف.
حضرتك تطرقت الى البيزو اكتويتر والكويل اكتويتر، ايضا على عجاله اتمنى ان توضح لنا الفرق بين الاستخدامات. والنقطه الاخيره اللي اسال عنها، خلال الديورنج تقول يصير عندنا عمليه سكراتشنج. اذا احنا عندنا عمليه بنتريشن عموديه، سكراتشنج ليش ده يحدث عندنا؟ اشكرك دكتور.
جود شكرا جزيلا. دكتور، الاكتويتر اللي نستخدمه بالنانو اندنتيشن هو only to create the motion. يعني انت بس تريد تسوي موشن. فبعض هاي الصوره انا ماخذها من شركه اسمها نانوفيا. نانوفيا تقول اني احسن من البقيه لان انا استخدم بيزو اكتويتر، فانطي لود، يعني انطي homogeneous load افضل من اللي يستخدم كويل اكتويتر. يعني هي يعني their point of view، ويثبتون هذا بالنتائج مالتهم، يقول انا هاي النتائج مال غيري وهاي النتائج مالتي. فالاكتويتر هو matter of applying motion. So يعني انا حقيقه ما اعرف شنو هو الاكتويتر. انا لا اعرف انه البيزو هو الكتريك انرجي تتحول الى موشن انرجي، والكويل هو ايضا الكتريك انرجي applying magnetic field and moving the arm here up and down. هذا كله نعرفه عليه.
دكتور الاكتويتر، العفو دكتور، الاكتويتر هو عباره عن سلندر وبستن ورود.
تمام.
بس اكو اكتويشن ميثودز اللي هي مينز اللي هي اما بالبيزو واما بالكويل. التايم اوف ديلي بالنسبه للسيجنالز اللي راح تتوفر البيزو افضل يكون بهذه الحاله.
تمام. اذا الكلي ماتهم صحيح، هم البيزو اكتويتر الكلي ماتهم صحيح. تمام. دكتور سؤالك الثاني كان على شنو؟
بالنسبه للسكراتشنج.
سكراتشنج. السكراتشنج دكتور هذا
عن السكراتشنج يعني.
اي دكتور احنا النانو اندنتيشن هو شنو؟ اندنتر واحنا نضغطه على السيرفيس، مو تمام؟ فعندي اللود سيل هي 1 دايمنشن، بس الاكيورسي مال المشين خلت الباحثين والمانيفاكتشرر both of them الريسيرشرز والمانيفاكتشرر يطلبون اكستنشن لهذا التست. فايش سووا؟ بدلوا المانيفاكتشرر بدلوا ال1 دايمنشن لود سيل ب2 دايمنشن لود سيل، وبدل ما اسوي فقط قوه عموديه اسلط قوه عموديه اسلط قوه عموديه وبعدين اسلط قوه افقيه. تمام. فالاندنتر اول مره يجي يلامس السطح فتصير قوه صفر، بعدين يبدي يتحرك على السطح في مسافه معينه with increasing load. تمام.
الغايه من حساب السكراتشنج، الغايه من السكراتشنج.
السكراتش كلش مهم بالكوتنج. انت تعرف يا لود يسوي ديليمينيشن.
تمام.
اي لود يسوي ديليمينيشن، اي لود يسوي فيليا. احنا نشوف هذا شلون صاير به هذا فيليا، هذا شلون صاير به فيليا. هذا كله الكوتنج كله دي اليمينيتد وداخل على السبستريت. دائما الكوتنج يصير يعني بعض التطبيقات الكوتنج هاردر ذان السبستريت، فاذا نزال السبستريت الكوتنج راح يصير عندك دبث عالي بالسبستريت لانه الهاردنس مالته اقل. وهاي كلها تعاريف يعني تعطيك الوركينج ليميتس فور ذا كوتنج. يعني انت تعرف اذا صار عندك مثلا هاي الاكوستيك ايميشن لما تطلع عندي او لما يصير عندي زياده بالفريكشن او زياده كبيره بالدبث، هذا يعني شنو صار عندك فيليا. فهذا اللود جو هذا اللود يو ورك سيفلي. بعد هذا اللود انت لا لازم تسوي موديفيكيشن. اذا كان اللود acceptable for you هاي اقبلها، اذا كان اللود unacceptable for you you need to redesign your coating.
يعني هذا حتحدد من خلال قد الثيكنس مال الكوتنج.
يعني هو مو الغرض الثيكنس مال الكوتنج، الغرض اللود اللي يسوي فيليا. لان هو السكراتشنج تيست الفكره مالته الاساسيه هو يبدي من زيرو لود. انا عندك هاي النقطه اللود صفر،
نعم،
وبعدين يزيد الى ان يوصل للماكسيمم لود. فوين صار عندي فيليا هذا معناته انه هذا اللود هو اللي سبب الفيليا.
واضح. شكرا دكتور حبيبي، شكرا جزيلا.
اصمم بحيث انه يصير عندي اللود الابلايد لود ان ابلكيشن ليس ذان ذس لود.
واضح. شكرا جزيلا الله يبارك فيك. شكرا.
الله يحفظك دكتور. الله يسلمك.
اذا عندنا اي سؤال دكتوره ذكرى تفضل. يعني دكتوره ذكرى تفضلي.
السلام عليكم ورحمه الله وبركاته.
وعليكم السلام ورحمه الله وبركاته.
جزيل الشكر لجهودك دكتور على هذا العرض الرائع. يبدو انه الدراسه اللي قدمتها حضرتك هي دراسه دكتوراه، لانه شغل ما شاء الله عليه. فأنا حقيقه دكتور يعني عجبني اسال بعض الامور، خلي ادخل على الاطار العام، اترك التفاصيل مالت الشغل. فقط ابدا افتي انه هذه نيو ماتيريال هي اندر الاستيك ماتيريال، مو صحيح دكتور؟
العفو شلون؟
الاستيك ماتيريال.
يعني هو احنا البرزنتيشن كان على التكنيك without concerning about the material. احنا الماتيريال اي ماتيريال نقدر نفحصها بهذا التكنيك. يعني اي ماتيريال اي كوتنج اي سيرفيس تريتد ماتيريال نقدر نستخدم التكنيك حتى نسوي كاركترايزيشن للسيرفيس.
اني سيرفيس يعني
اني سيرفيس حتى البولك سيرفيسز يعني هسه كان اكو فد ديبيت بالساينتفك كوميونتي حول هل النانو كاركترايزيشن اوف ذا ماتيريال represents the micro characterization of the material، وهذا الحل من فتره طويله، وفعلا وجدوا انه هذا النانو كاركترايزيشن gives even more accurate results. يعني الريزلتس اللي جايه تطلع عندي بالنانو سكيل هي اضبط من الريزلتس اللي جايه تطلع عندي no error if the experiment set correctly there is no error.
ما شاء الله. تمام دكتور الله يحفظك. بس اكو فد سلايد قريت يعني الاستيك والبيلاستيك، بس ذكرنا بالتفاصيل مات هذه الماتيريال. what's the difference between
العفو هذا السلايد
الاستيك؟ لا اعتقد اول سلايد.
تمام هذا اللي هو
الاستيك والبلاستيك. نعم.
الفكره دكتوره والضعف اللي عندنا ببقيه التست انه انا حتى اذا دخلت بمنطقه البلاستيسيتي، يعني انا سلطت لود على الماتيريال وصار بها فيلير، صار الديفورميشن اللي صار بها صار بلاستيك ديفورميشن. بس بالحقيقه انه حتى بهاي المنطقه، حتى بعد الفيلير، حتى بعد البلاستيك ديفورميشن اكو الاستيك ديفورميشن.
ما شاء الله. تمام دكتور. زين اذا الموضوع الموضوع هل هذه التكنيك هل نقدر نحددها فرضا نقول فقط على نشتغل بها فقط على الموصلات، على اشباه الموصلات، على العوازل، لو انت تقول any surface
for everything
for all. Okay thank you so much دكتور. thank you so much and thank for all.
هذا اهم سؤال شاب، هاي فد مقارنه بسيطه. شوف هسه هذا الكيرف.
نعم بالضبط. اريد اعرف ليش بذلك لذلك اريد اقارن بين الانواع مالت الماتيريال.
هذا الكيرف ايش يعني؟ انه الالاستيسيتي بهاي الماتيريال، الالاستيسيتي بيهافير بهاي الماتيريال under this particular load is high. يعني انا عندي الكونتريبيوشن اوف ذا elasticity. خلينا نرجع هنا هذا احنا لما نسوي اندنتيشن ندخل هذا الاندنتر بالسيرفس، تمام، ونبدي ندفع به الى ان نوصل الى قمه اللود اللي انا مقرره، يعني خلينا نقول 10 ملي نيوتن. بعدين لما توصل للقمه ابدي ارفع اللود. فاذا الماتيريال بيها الاستيسيتي ايش راح تجي؟ راح تصعد ويا الاندنتر، راح ترجع ويا الاندنتر. انا مو ضاغطتها، صار بها بلاستيك دخلت بالبلاستيسيتي. بس within the plasticity there is an elasticity. فلما ابدي ارفع الاندنتر lifting up للاندنتر، الماتيريال يصير بها elastic recovery، ترجع تستعيد بعض بعض الدايمنشنز مالتها. فهذا اللي هنا هو elastic recovery of the material. يعني هاي المنطقه هنا هي منطقه الماده قدرت تستعادها بعد الاندنتيشن. يعني الاندنتر دخل خلينا نقول 100 نانومتر، بعدين لما طلع الفاينل امبريشن كان بس 50 مايكرو نانومتر. فهاي ال 50 الثانيه السيرفس قدر يستعادها، لان هو عنده بلاستيسيتي، بعده بلاستيسيتي. بينما هاي الماتيريال مثلا شوف most of the deformation is plastic. هاي المنطقة هنا تمثل البلاستيك deformation، هاي المنطقة هنا تمثل الالاستيك deformation. فهذه هم طريقة اقدر اعرف a particular load، يعني في اللود معين اقدر اعرف مثلا اقارن البلاستيك ويا الميتال، ايش قد بي هذا الاستيك ريكفري، هذا ايش قد بي الاستيك ريكفري.
تمام. عاشت الايات.
طبعا دكتور الحديث عن النانو اندنتيشن يحتاج محاضرات طويله. يعني احنا هنا
جبنا دكتور. نعم انا انتبهت انه اختصار لكل شيء، لذلك يعني يحتاجين ان نسال بعض الامور. اذا ما معناه دكتور اذا هذه التكنيك يعني حسب هسه هذا بالبدايه التكنيك هذا ويا الميتال ويا ميبي السيمي كوندكتور افضل مما هو مع العوازل، ممكن يعطي نتائج اكثر.
لا نفس الشيء دكتوره، نفس الاكيورسي، وهي البتلز وهي السيراميكس وهي البوليمرز فور ايفريثينج ماكو اي فرق. يعني هو يستخدم بالتاير اندستري بصناعه التايرات، ويستخدم بالسيمي كوندكتور اندستري، يستخدم بالثين لود عفوا الثين كوتنج هذا نعم الثين فيلم يستخدم في الثين فيلم، فيستخدم فور ايفريثينج.
ممتاز. جزيل الشكر دكتور، جزيل الشكر لجهودكم الطيبه، الله يحفظكم.
شكرا. اذا عندنا اي سؤال اساتذه او مداخله، إذا عندنا أي سؤال أو مداخلة من الأساتذة الحضور.
طبعا أنا أعتذر مرة ثانية إنه صار الشرح يعني كونسبتس هواية وبسرعة، فيجوز